This example is going to be doing glitch attacks with the ChipWhisperer. So this follows along one of the example tutorials fairly closely. So there's this glitch attacks tutorial, and it goes on how all this works. So this is what sort of we'll be going through. So to begin with, what are glitch attacks? Well, glitch attacks basically exploit the fact that systems expect a reliable clock generally. So they do stuff like to speed up data. We on the first clock edge we say, for example, load a piece of data. Now on the second clock edge we're actually executing that data. While we're executing it, we can load what we expect the next piece of data to be if we increment the program counter. So we can have this sort of pipeline system that lets the microcontroller execute code faster than if it had to load one data, execute it, and then go back and load data number 2. So most of the time this works. Obviously, if you do a jump or branch, it may or may not work because you might have loaded the wrong code. But so if we have a glitch, consider this case here where we load the first instruction as before. We have this really quick clock edge, but it just sees it as a clock edge. So it goes, okay, load instruction number 2 and begin executing instruction number 1 just as before. But very shortly after that, we get a second clock edge. And so we actually, then it starts to execute the second instruction, and then load the third one. But what's basically happened is it hasn't had time to execute instruction number 1, so it skipped over it. So we can use this to skip certain instructions in the microcontroller, or sometimes do other effects. It's a little bit of chance, like nothing's quite as deterministic here. But they can be quite powerful. So if you look at authentication code, often you have some higher level module that basically just says, okay, well, is this person authorized or not? So this example is pulled from the Linux util module, which has this authorization code in it. And you can basically see that if we could skip over this, if the user ID is not equal to 0, check all this stuff. If you could skip that one check, it would just return true. So it's quite powerful. All right, so let's get on with it. So the ChipWhisperer itself has this glitch hardware that uses 2 adjustable phases. So you'll see you have 2 options for adjusting the width and the offset of a glitch. So we have an input clock, which is the original clock either from the device or generated by the ChipWhisperer. And then we choose to shift this clock a little bit. And this is the phase shift number 1. And then we shift it a little bit more. This is phase shift number 2. We do this and with the inverse of one of them to generate this glitch stream. So this glitch stream, the width of this glitch stream, you can see is basically the difference between the 2 phases of these clocks. So this is what phase shift number 2 does. This tells you the width of your glitch. And we can also offset it from the beginning of the input clock. So the input clock is what's fed to the device under test. So this gives us an adjustable phase from the device under test and an adjustable width of the glitch. Now what we can do is we can choose how to use the glitch. So there's this mux, and you can either, you can output just the glitch if you want, so if you just want the glitch stream, or you can do stuff like XOR the glitch with the clocks. You get funky looking waveforms here, and the objective is to basically end up with something like that. So there's a little bit of a trick in how this is done that you need to know a little bit about. And this is that it uses partial reconfiguration of the FPGA. This is a fairly advanced feature, and it requires that basically the FPGA itself loads a special bitstream file, and this bitstream file tells the FPGA its configuration. Normally you would fix that, and these phase shifts you could do through adjustments on some of the blocks within the FPGA, but due to some limits of the FPGA, we can't do that. And what we actually have to do is reconfigure a portion of the FPGA in real time. So this requires some additional files. They all ship with the ChipWhisperer system, and they're called these ChipWhisperer partial files. So there's this S6LX25 glitch width and glitch offset.p. But why this really matters is that the files are keyed to the bitstream, and there's a script that generates them, but it takes 6 or more hours to generate them. So if you change the bitstream, so for example, if you have reconfigured the Xilinx project, then you will no longer have access to the partial reconfiguration feature. It just automatically gets disabled if these files differ from the expected bitstream file. So basically it uses the date the files were created. It's a very simple way of doing this. So that's done to prevent possible damage to the devices. So if you do not have the partial reconfiguration files, you won't have this glitch which as percent a period. There's also, so the glitch width, there's two options for the width of the glitch. There's this percent a period, which as you would sort of expect is based on the actual period of your clock, and it scales with the clock. The fine adjust is just a fixed number, but that only gives you about plus minus 5 nanoseconds adjustment. What matters for a lot of our stuff is, for example, if we have a 7.37 megahertz clock, you'd have a period of 136 nanoseconds. So that's not very useful. 5 nanoseconds, you're barely giving yourself any adjustment range. So I just want to point that out because if you go to use the system and you can't access these, it might be that there's some configuration that's screwed up in your installation, and maybe you need to copy these files from the release or something. All right, so that's enough of that. Let's get on with it. So the first thing you're going to do is look at the glitch example. So I'm going to open the WinAVR prompt. And in this case, I have a special batch file that opens WinAVR. All you have to do is, you need AVR GCC. So this is going to compile the C code. So let us, and I'll change directory to where I'm holding the example. So I have this huge directory here. But inside this, there's this glitch example.c, which is the file we are interested in. So let me go ahead and pull that over for you. So here's glitch example.c. So this file contains what we're going to glitch. So in the main, it basically it sets a trigger pin low, initializes a UART, prints hello. It has a bit of a delay before it calls whatever function we call. And in this case, we call glitch 1. So glitch 1 just goes into an infinite loop. So this loop a is not equal to 2. Well, somewhere we set a equal to 0. So that should never happen. It's not possible. And what we want to see is can we break out of that loop? So let's begin there. So again, I'm going through this example. Here's the hardware setup. So basically, you need to connect the FPGA out pin to the clock net. We're not using this oscillator at all. That's totally disconnected. So otherwise, it's the same type of setup as you would have used for the side channel analysis platform. So I have the hardware set up here, and I'll run the ChipWhisperer capture. Let me just find it here. And then we'll go through this example. Where is it? All right, there we go. So I just run my regular ChipWhisperer capture. Make this window bigger. All right, so you need to configure the scope as the ChipWhisperer OpenADC. We're going to set the target to the simple serial, and again, these are all, everything goes through here, so if you want to follow along, you can sort of move it so you can see both. And then you set the target setting as the ChipWhisperer, and that baud's fine, everything like that's fine. If you haven't already, you'd have to download the firmware. I already have the FPGA program, so I don't need to do that. And then we connect on both the scope and the target, or I can actually just use the master here. So everything looks good. Now the other thing we need to do is we're going to open a terminal. So this will let us see the output of the AVR, and I can just hit connect. So the AVR itself won't run yet. The problem is that there's no clock to the AVR, right? I connected that clock gen output, so I'm going to move that window out of the way for now. So I've got to go to the scope settings, and I've got to set up the clock. So we have this clock gen settings here, and I can basically just program it with my desired 7.37 7.37 megahertz clock frequency. It figures out some divisor values, and you can monitor the frequency here if you want. And we're not going to use the ADC right now, so we don't care about that. And we need to tell the glitch module that we want to use the clock gen source. So this will pass a clock to the glitch module, the 7.37 megahertz clock. No glitches are going to be inserted because it's set to manual. And finally, we're going to set this target HSIO out as glitch module. So now we have a clock that's routed into the glitch module, and from the glitch module it goes out to the target board. So now we have a clock, hopefully, running on the target. So you can see that is here. And we now that we have a clock running, we need to program the AVR. So we have AVR Studio open here. Let's connect to the AVR programmer. And you can hit read signature. So that worked fine. So things are working. If you screwed up, so for example, if I forgot to do this, then you won't get, it'll fail because there's no clock. So you need to make sure you have a running clock and the jumpers are set correctly. Okay, so now I have the hex file that I would generate. So we need to make that hex file. So this is the WinAVR prompt I opened. If you remember, it had AVR GCC and everything, so I can use make. When you type make, you need to specify the MCU for these make files because you could use other devices. So I just use ATmega 328p, and it builds your hex file. So now we program that in, so you can see I just made that now. Program, and success. All right, so leave this window open because we're actually going to use this to reset the AVR. Every time we hit read signature, it'll reset the AVR. So we use that because we're going to be glitching it. It's going to go into some invalid state. So we're going to use that a lot, actually. So let me move the instructions out of the way so they don't confuse you. All right. And here's the capture window. So what you will see is this is the terminal window I opened. And every time I hit read signature, notice it says hello, there's a new line, and then it prints A. So if you look back at the source code, you can see that is what we expect. So output char 0, so it outputs a single character, the A. It pulses a line high and low, and then it's just an infinite loop. So we want to get out of that infinite loop somehow. And we're going to get out of it using the glitch module. So the first thing you need to understand is what the glitches look like. So let me pull over the example from the documentation here. So the original clock we're using is a 7.37 megahertz clock. And the glitch system either XORs with, so if we scroll somewhere up here, we have this. So we can either insert glitches inside the clock itself or right in front of the clock. So what we're going to be mostly using in this example is glitches that look like this bottom part here, where we have the original clock and we insert a short glitch right in front of it. So to get this, we're going to go ahead and set the glitch module up at the bottom here. Where is it? Right here. So I just had some values that I found. Around 8 worked and -10. So -10 is critical. The negative means we're going in front. So again, this like this. So we have a negative offset. And we're using the percent of period, not the fine adjust. So double check those carefully because it can be frustrating if you choose the wrong ones. All right, so there's a little window here. And if I hit manual trigger, so we only set a single glitch every time I hit the button. So if I hit manual trigger, you can see it just reset. And you can try different things. Eventually, so Oh, there we go. So actually what's happened is we've glitched out of that loop because now we see A1, 2, 3, 4. And you can sort of, at this point it goes into an infinite loop. I mentioned you had to keep this AVR Studio window open. So you hit read signature and it leaves the program node. So there we go. And we see hello A again. All right. And you can, every time you do it, it's rebooting. And you can try hitting manual trigger, so there it's just reset. So sometimes it'll reset. Ideally, you want it to just glitch out of the loop. So there you go. There's A1, 2, 3, 4. So you can sort of play with some of these settings a bit. And you can try to get the most reliable glitch. Let's go down and glitch width. And see. Oh, so there's a bit. So I don't know if that's more reliable or not. And you can play with, for example, how many glitches to send. Oh yeah, so 2 seems to work. So the one thing to be careful about is that remember you can get the AVR into invalid states. So you may want to use the read signature to reset it frequently. Yeah, because some of the invalid states, it just won't respond. And it may look like it's still in that infinite loop when really it's never going to respond. So anyway, so you get the idea. You can play around with that. So that's sort of a simple example of using the glitches. So what we would like to do next is use automatic triggering. So the glitch module down here has a few triggers you can select. So you can trigger on an external I/O line, and if you trigger on the external I/O line, so these are related to the ADC triggers. The ADC trigger you can trigger on rising edge, falling edge, high or low. The glitch trigger you can only trigger on a rising edge if it's an external I/O pin or a digital I/O pattern or the sound absolute difference analog trigger. So you can select between any of those and then it becomes a rising edge, or you can use this manual, so that button I was pressing, and there's a continuous mode where it just always outputs the glitches. So it's a tiny bit different from the analog trigger, but hopefully that makes sense, and we'll go through this example. So we want to do the glitch 1, a bit of an automatic trigger. So the glitch 1 is very unexciting. It's this loop here, and we have this high-low, so there's a positive going trigger pulse. So let's move this window out, and to use this, first we're going to set the glitch trigger to external trigger, and the trigger pins, we're going to make sure we select just IO4, so trigger line. And if you have a scope, by the way, you can enable this trigger out on front panel A, and you can connect a scope line to the front panel trigger pin, the positive pin, and you can see when your trigger is occurring. So this can be really handy for debug because you can confirm when the glitch should be being inserted. And this stuff doesn't matter because we're not using it anyway. And you do need to make sure the trigger module is basic, so edge level, because that's used by both the analog and the digital trigger. All right. So now what should happen is automatically when I reset the AVR, it will trigger on the code where it says trigger high. So right here. So we want to insert some glitches, and before I was using just one glitch, but I'm going to change that a bit. So I'm going to say change the repeat to 5 glitches. Let's see what happens. So what you can see is that it says hello A234. So it's actually automatically glitching over that loop, and in fact glitched past sending the 1. So that was an automatic glitch. Every time I reset, it more or less does a glitch, and occasionally it's rebooting a few times here. So you can sort of play with these. Oh, so there we go. That's almost a perfect glitch. There's a few where it reboots, but you see it says hello A, so it should go into an infinite loop here, but it doesn't. It glitches past that automatically and goes 1, 2, 3, 4. So what we're using there is the simple trigger capability, but real systems aren't going to have, you know, that serial IO line trigger. So, or that, not the rising edge, you know, they're not going to have a line that conveniently goes high right when you should glitch them. So you need to use other stuff. So the first thing I want to do is I want to show you how do you even know that glitch is triggering. I mentioned you can use the front panel A. The other thing you can do is actually set up the analog capture to trigger on the same trigger. So to do that, you have to make sure you set the mode. So this is the trigger setup for the power measurement to rising edge. I'll need some gain on my analog ADC. I'll say like 30. And we need to select a clock for the ADC. So I'm going to use the generated clock, so the 7.37 megahertz clock, and multiply it by 4. Here, note DCM locked is not checked. So you have to hit reset ADC DCM. It should lock and it should get 29.5 megahertz. So if I hit capture, you'll see the ADC will now wait for the trigger, and after a few seconds, it'll give up and timeout. So there goes timeout, trigger forced. So if our trigger is working, what we can do instead, and let's get it so you can see all windows, is I'll hit capture here, and then I'll go here and hit read signature. And right when I hit read signature, it triggered, and there's a warning because it was expecting some special data back, but it never got it. But that's fine, we don't care about that. And we can see we've repeatedly gotten the trigger, and the trigger event is actually capturing. There's a bit of an uptick in the power consumption because this is where that IO line went high right there. So that's sort of what you'd expect, and then it goes low, and you see that. So it's easy enough. Let's go onward to the fancier trigger. So the fancier trigger, again, it's all in this tutorial documentation, is the serial IO line trigger. So here, we're going to not use that cheating. We're not going to use that trigger line, but we're actually going to trigger on when the device under test sends this A back. So in the code, you can see that it sends an A, and then the trigger line goes high, then the trigger line goes low. You go into an infinite loop. So we want to trigger right here because, you know, in a real system, you may have it send a prompt like, you know, waiting for password or system locked or something like that. And we want to use that to trigger it. So to do that, we've got to do a few things. The first thing we do is we change the trigger module from basic edge to digital pattern matching. So that's critical. That enables the digital pattern matching. The digital pattern matching module, we're going to use the IO lines. And these idle high normally. They're sort of a TTL serial logic. So select the collection mode to AND. This means it's ANDing together the lines. If either of them goes low, the output will go low. So because it's only one of these lines is used at a time, this works fine. It's a simple way to condense them. This way we could trigger on data to or from the device under test if you wanted. And finally, we have this digital trigger pattern matching. So right now it only works with a single character because of the basically the intersymbol timing isn't repeatable. If you wanted, you could trigger on a long sequence, but you would need to know exactly what that sequence would look like. So I just trigger on the A pattern for a 38400 baud. You can see it's actually triggering continuously almost here, it looks like. So let's go ahead and disable the trigger for a second. So you can get into a bit of a loop here because if it triggers and resets the device and the device resends A, then you can see what's happening. It resets it, the device sends A, it glitches it, but if that glitch is just rebooting the device, well then it sends A again, glitches it, so it's as soon as you enable it, the glitching will happen all the time. It doesn't wait for you to do a capture event. So let's see that. So I've turned it off right now, so I've sort of broken that loop. And you can do external trigger. If you want, you can just send a bunch of new lines. They'll be ignored by the device, and that'll clear the window. So we have the external trigger set up, and if we want to test it's working, we can again use this trick about the analog capture. So we have our read signature. This will reboot the device. I hit play there, and then I hit read signature. And you see right away you get this this capture trace. So in this case, it's actually it's triggering a little bit earlier, so it's sort of triggering probably right there. We see some of the power due to the IO line going high, low and then high, I guess, or high and then low, sorry, and then we see some other activity afterwards. And this other activity is in fact probably the system rebooting, because we see that it's doing this loop here. So we're not quite glitching it correctly. So let's reduce the repeat to 1. Okay, do this and set it back to external trigger. So now it's automated. We'll do read signature. So it did not glitch the system, it just stayed at the A. And we can try it a few times to see, nope, it's not working. So let's just increase the repeat. So now we have so we went into that infinite loop again, and I just changed it to only send. So instead of switching to manual, I said just send one glitch, which I know doesn't seem to cause that infinite reboot loop. So at this point, it's sort of a more or less an experimental system to determine what good glitch settings are. And you will eventually be able to get ones where, based on the IO line trigger, it's glitching through to the 1, 2, 3, 4. So there we go. You see. So now we automatically got a 1, 2, 3, 4. So this is based on a glitch that uses the IO line trigger. And as you can see, I did have to fiddle a bit with some of the settings. So this is sort of normal, what you'd expect. And you ideally, you don't want it to just reboot. At least in our case, maybe there's situations where that you do want it to do. So you just have to play with it until you get the proper settings between the glitch width, the glitch offset, and the repeat. All right. So what else can we do? That's the first part of the tutorial. The next part is I'll look at a little more complicated functions. So the next function I look at in the example is one where we compare a received character to either something like a Q and we output 1 or 2 or not. I'm actually going to skip that, and I'm going to jump right to the fun one, which is glitch 3. So glitch 3 is basically a password comparison. So how do we do this? We go back to glitch example, and we go ahead and look at the function glitch 3. So glitch 3 receives in a password, checks if it's touch, and if it's touch, it sends either back bad or welcome. Now, as a note, I've tried to avoid timing attacks. So what I've done is I've always compare 5 characters of the password. So, it doesn't check for too long a password. It's a very dumb check. But the time between when you send your password and when it sends back bad or welcome is always constant. It doesn't matter, if the first character is wrong or the last character is wrong only. It's always going to take the same amount of time for that comparison. So this eliminates the timing attack. And how I do this is I assume the password is okay at the beginning, and then once it's wrong, I set this variable to 0, and then it checks this variable. So that's a very simple way to do it, but fairly reasonable. It's not insane. So we need to modify in main to call glitch 3, and then I make it again. And then I'll program this in. Very important note, when you go to program, make sure you disable the glitch. The problem is that you could so just set it to manual, we'll disable it. What could happen is that when you're programming, you could still have the glitches running, or for example, when you're programming it will float that IO line, and that could cause the ChipWhisperer, because it automatically glitches regardless of if your capture is armed or not. It could cause it to glitch the clock, and it'll screw up your programming. Very frustrating. So there we go, we're programmed. So now when it comes up with this C. And if I type in touch, it says welcome. And then it's just in an infinite loop, that's all it does. So we have to again use our read signature hack, not hack, system to get it. So if I type in any other password, it just comes back with bad. So what is this? Bad. It always just comes back with bad. So what we want to do is glitch out of this problem. So one thing you might do first is in actual manual mode, right at this prompt, you could try, what happens if I just glitch out of that loop? And you could sort of play around with this for a bit and see if you can glitch through it. But it may or may not be successful because you have to glitch through quite a bit. So maybe I need to do 30 glitches in a row. And it always is just seeming to be rebooting. And you do have to play with this quite a bit, so see if you can get it to work. But what I'll show you is sort of using that automatic glitching. And I'm going to use the basic IO line trigger for now. It's just a little easier to demonstrate. But as you can see, the digital pattern matching also makes it quite reasonable to do. So you could glitch on the data you send back, on the new line you send back, for example, would be a good one. So instead I'm going to glitch on the IO trigger line, going high, and if you look at the code for touch 3, what you'll find is that before this loop here, it goes high. So after we've received in all the variables, the line goes high, which would basically be after you sent the new line, because you'd receive the new line and then it would say, oh no, that's a new line, skip out. All right, so we've got that set up, and as before, let's reduce this, let's say 4 glitches, and we set it to external trigger. Just do read signature. Now remember, these glitches won't happen until I put a password in. So I put in bad, it comes back bad. And if I do touch, it's still working. So the system's still more or less working. So this again requires quite a bit of experimentation. So let's try something like 15. Test. Oh, so we can see it looks like it reset here. And then came back with bad. So you do get some weird stuff. Oh, came back with bad. And you can also check, for example, if I put in the right password, oh, it just rebooted. So now it's still bad. So even the right password is sort of screwing it up. So there's some glitching going on, and you may have to take out a few examples. So maybe this is too much. Let's try 12 glitches in a row. And always reset it, because you might be in some unknown state. So we're getting a bit of a reboot. And there we go. So I put in the test and it came back as welcome. So this was a successful glitch attack that would have effectively broken the authentication code, because it skipped the password check, but then the system went back to normal operation, because the repeat's very short, so it's only doing 7 glitches in a row, and it was still able to execute. At this point, it's back to executing regularly, so it output welcome. And normally this would go on to display your menu or whatever. But so that's sort of a fun example. That's showing you how glitching in real systems could give you access to them. So there's lots more you can do. You can look at glitching other examples. So go on, look at bootloaders. You can look at download example bootloaders, app notes, and program them to the microcontroller. Pull in authentication code from embedded systems and see how vulnerable it is to this type of glitching. And of course, you can look at moving all these glitches to more real triggers. So this would be the digital pattern matching trigger, or even cooler, you can do the analog, the sum of absolute difference trigger. So that's a more advanced topic. There's another video that deals with how to use that. But hope you found this useful, and thanks for watching.